Hello once again to the exam solutions for A-level physics. This is an AS level question paper. We're going for AS1 and this is the summer of 2011. So it is a question on projectile motion and we're looking at when a long jumper completes a jump. The centre of mass is 1 metre above ground level at takeoff, 0.4 metres above ground level on landing. So let's have a look then at the first part of this question. Sketch the path of the centre of mass of the long jumper from takeoff to landing. Now, with projectile motion, all of the paths are going to be parabolas. So our parabola in this case starts where he takes off and goes a bit further down because his landing point is further down than his takeoff point. Part B then, the long jumper has studied some physics, as all good long jumpers do, and has read that in order to make the horizontal distance of his jump as long as possible, he should jump at an angle of 45 degrees to the horizontal. So if he takes off at a speed of 9.3 metres per second at an angle of 45 degrees to the horizontal. And part 1 says calculate the initial vertical velocity of the athlete. So let me just sketch what that looks like. There's our 9.3 metres per second and it is at 45 degrees to horizontal, and we're looking at, well, what is the vertical component of this? We want to know what the vertical velocity is. So in fact we're going to use some trigonometry to find out that vertical, and it is 9.3 sine 45 degrees, which calculates to be 6.6 metres per second. So I've gone for an accuracy of 1 decimal place because of our speed was given to 1 decimal place. Part 2, show that the vertical component of the velocity of the athlete on landing has magnitude 7.4 metres per second. Now, one of the tips for looking at projectile motion is to split up the motion into the vertical and the horizontal. Now, it's already said to us about the vertical, so it is in fact the vertical that we're going to consider. So we want to know what the velocity, whenever it reaches here, is going to be. We need to use a little bit of our knowledge of the parabola and the shape that it is to help us with answering this. And what we're going to do is we're going to ignore actually part of the journey. So the velocity that the vertical velocity that the long jumper has at this point is in fact the same magnitude as the velocity that it has there, except it's going to be in the opposite direction, of course, because it's going back down. So we're going to use that as our velocity, our initial velocity, and then he'll be accelerating down to this point. Now, as well as that, we then can see what our displacement is, and our displacement, the distance that he travels in that part, is 0.6 metres as he goes from this point of the journey to here. So we're going to use all of that to help answer this question. So we're only interested in the vertical, and whenever we're looking at the vertical, it is an acceleration due to gravity, so we're trying to find the velocity in this case, and we've got the initial, which is 6.6, and if you remember we said it was going to be negative because it's going down the ways. We have the acceleration, which is minus 9.81, and the final thing is our displacement, which again is negative, and it's 0.6. So we're going to use an equation of motion, our v squared equals u squared plus 2as. Let's put our numbers into that, so we're trying to find v squared in this case, and minus 6.6 all squared plus 2 times minus 9.81 times minus 0.6. So let's fire that all into the calculator, and that gives us 55 0.332, and our v is then going to be the square root of, well, we have to do the square root of 55.3, which is equal to 7.4, and that is what we were trying to prove here. We're trying to show that. So the vertical component is 7.4, and then we have our 7.4, which is probably firing meters per second there. Part 3, the final part, is to calculate the time spent in air by the athlete during the jump. And again, let's look at the diagram for this. And what we're going to do is we're going to find the time of flight to the top, to the highest point. We're going to double that, and then we're going to add on this second part here, or this last part here. So time of flight to the top, and that is the same as the time of flight to get to here, and then we're going to add that second part on. Now at the very top of the flight there, the velocity is in fact 0 vertically, and whenever it gets back down to here, like I've already said, the velocity is the same as what it is here, but in a different direction. So let's do that calculation now. Again, it's all about the vertical that we're interested in. So our first one is trying to find the time of flight up to the peak, alright, the top part. So that's where our velocity is 0. Our initial velocity is 6.6, and our acceleration due to gravity is minus 9.81. So the equation of motion we're going to use is v equals u plus at. Let's fire in the numbers there. 0 is equal to 6.6, and this is going to become minus 9.81 t. So t works out to be 0.67. So fire that in there, 0.67, which really we can only write as t is 0.7. Now the second part that we needed to do, we go back up here just to remind you. So we just worked out this part here, so we need to double that. So it's going to be 1.4 to here, and then we've got to find this last section here. So let's move back down to find out that last section. Tell you a wee bit about what's going on there. Well, we're trying to find out the time. We've been given the initial, which was minus 6.6. The final was minus 7.4. And acceleration due to gravity is minus 9.81. A lot of minus signs there, and we're still using v equals u plus at. So our minus 7.4 equals minus 6.6 minus 9.81 t. So rearrange all that, and we end up with t is equal to 0.08. Now you really have to write that to the same accuracy as before, so this is going to be t is equal to 0.1. So total time is equal to 2 times 0.7 plus the 0.1. So that's going to give us 1.4 plus 0.1, which is 1.5 seconds. Just put that in, 1.5. There we go. Tick.